So, what you're looking at here is pretty much the foundation of all modern AI, the neural network. Today, we're going to break down how this digital brain actually works, and specifically, how we can teach a machine to do something that feels so simple for us, but is also incredibly complex. And that's just to see.
Okay, let's start with a really simple test. Your brain, my brain, we instantly know this messy, low-resolution number is a 3, right? We can recognize a 3 written in a million different ways without even thinking about it. But for a computer, this is a surprisingly difficult problem. And that's really the heart of the challenge. I mean, imagine you sat down to write a program to recognize digits. You'd have to create this impossibly long list of rules. Like, what about a 3 with a flat top? Or a really loopy one, a slanted one? The task just explodes from being super simple for us to frighteningly complex for code. This is why we need a completely different approach. So instead of trying to write a million rules, we build a system that can learn the rules on its own. And that system starts with some pretty basic anatomy. You've got neurons and you've got layers. First up is the neuron. Now, in our digital brain, we're not talking about complex biology. It's much simpler. It's basically just a container that holds a number between 0 and 1. A good way to think about it is like a single grayscale pixel, where 0 is totally black and 1 is totally white. We call this value the neuron's activation. The higher the number, the more lit up it is. Now, these neurons aren't just floating around randomly in some digital soup. They're organized into these neat rows called layers. And when you stack these layers on top of each other, that's what forms the basic structure of our whole neural network. For our digit recognizing network, the structure is pretty specific. It all starts with an input layer that has 784 neurons. That's one for every single pixel in the image. It ends with an output layer of 10 neurons, one for each possible digit, 0 through 9. And then sandwiched in the middle, we have the hidden layers, which is where all the real magic happens. For this network, we're going to use 2 hidden layers, and each of those will have 16 neurons. So, we've got this layered structure. But why? What's the point of those hidden layers in the middle? Well, this gets to the absolute core idea behind deep learning. It's all about the power of abstraction. Let's go back to how we actually see things. When you look at the digit 9, what's really going on in your head? You're not consciously processing 784 individual pixels. No, instead, your brain brilliantly breaks it down into components. You see a loop at the top, and then you see a straight line kind of attached to it on the right. Just like an 8 is a loop on top of another loop, or a 4 is basically 3 different lines, or pattern matching machines. And we can go even deeper. That loop isn't just one single thing. It's really a combination of even smaller, simpler patterns. It's just a bunch of short, curved edges all arranged in a circle. This idea of breaking things down from complex to simple is exactly what we want the neural network to learn how to do. And this is the brilliant idea behind hidden layers. The raw pixels feed into that first hidden layer, and maybe that layer learns to recognize really simple things like tiny little edges. Then, the next layer can take those edges and learn to combine them into bigger components, like loops or straight lines. And finally, the output layer takes those assembled parts and makes a final decision. Hey, I see a loop on top of a line, that's gotta be a 9. Okay, so we've got this elegant concept of building up complexity layer by layer. It's a great idea, but how does the information actually get from one layer to the next? Let's dive into the mechanics of it all and look at the rules of connection, weights and biases. The way one layer influences the next is controlled by something called weights. Every single connection between 2 neurons has a weight. You can think of it like the strength of that connection. And fundamentally, these weights are what tell a neuron what specific pattern to look for in the layer that came before it. Let's make this super concrete. For example, let's say we want a single neuron in our first hidden layer to become a dedicated edge detector. We want it to light up, to get really active, but only when it sees a small diagonal edge in a very specific spot in the image. So how would we set up its weights to do that? Well, to make our neuron an edge detector, we would assign positive weights, you can see them here in green, to the pixels that actually form that diagonal edge pattern. Then we assign negative weights, in red, to all the pixels surrounding it. The neuron then does a quick calculation, a weighted sum, and it's only going to get a high positive score if the right pixels are on and the surrounding ones are off. That is how it learns to find its specific pattern. But there's one more key ingredient here, the bias. So after the neuron calculates that weighted sum, it adds this extra number, the bias. You can think of the bias as a measure of how willing that neuron is to activate. A high bias means it'll light up pretty easily, while a large negative bias means it needs a really strong signal from its inputs before it's willing to get active. It's basically an activation threshold.
So we take our weighted sum, we add the bias, and we get a number. But remember, we need a clean output between 0 and 1. To get that, we pass the result through what's called an activation function, like sigmoid. And all this function does is it squishes any number you give it into that nice, neat 0 to 1 range. That gives us the final activation value that we can pass on to the next layer.
Okay, so we've looked at all the individual parts, the neurons, the layers, the weights, and the biases. Now let's zoom out a bit and really appreciate the true scale of this machine that we've just built.
Get ready for this. For our simple network with just those two 16-neuron hidden layers, the total number of weights and biases, all those little adjustable parameters, is nearly 13,000. That's 13,000 different knobs and dials that can be tuned to change how this network behaves.
And while 13,000 parameters sounds absolutely mind-boggling, it really helps to remember this one key idea. At the end of the day, the entire network is just one giant, ridiculously complex function. It takes 784 numbers, our pixels, as an input, and after all that math, it just spits out 10 numbers as an output, telling us how sure it is that the image is a 0, a 1, a 2, and so on. So, we've built the machine. We've seen its 13,000 knobs. But that leaves us with the biggest and most important question of all. We can't possibly sit here and set all of those weights and biases by hand. So how does the machine learn? How does it figure out the perfect setting for every single one of those knobs all by itself, just by looking at examples? Well, that process is what we call training, and that's a story for our next explainer.